All right. Hello there, ladies and gentlemen. We are going to work on some equilibrium problems today. This is problem 12 in the workbook, I believe, if everything's going according to plan. We're going to work on some problems that just are a little bit tougher than what we've seen so far. There's some good information here up at the top, and it's really important when you're doing these kind of problems to think about the situation you're in. It's really important to notice whether the amounts you're being given are the initial conditions, what is being started off with, or the conditions at equilibrium. So that's a huge distinction that you need to make, and it's going to require different techniques depending on what exactly is going on. So it's really, really, really important that you pay attention to that kind of stuff, and that's what it's talking about right here. Now, I know this is a little bit hard to read, and I really want you to pay attention to the language. So what I want to do is I want to go ahead and let's work on these problems 1 and 2. Let's go ahead and enhance there. Okay, there we go. Now we've enhanced it, and we can just see problems 1 and 2. Again, that's on that same page. I just want you to be able to see it so that I can point some stuff out to you. Now, let's take a look at this first problem. It says, given the reaction A plus B yields AB, so just a simple generic reaction to start off with. Suppose 2.50 moles of both A and B are placed into a 2 cubic decimeter glass reaction vessel at 25 degrees Celsius. So that's actually telling us what we're starting off with. Those are the initial conditions. A huge, huge key word here is at equilibrium. So what it's going to tell us after that is the conditions that we're going to see at equilibrium, once the system has a chance to reach that equilibrium state. And so then it tells us something about the amount of B that's there at equilibrium. The technique we're going to apply here is something called an ice table. So what we're going to do right now, right off the bat, is get that ice table set up. And here's how we do that. I'm going to write the reaction in question here across the top. Like that. And we're going to make a little table. And I stands for initial, so that's going to be the first line of my table. C stands for change, so that's going to be the second line of my table. And E stands for equilibrium. That's going to be the third line of my table. So ice. And these are things that we're going to end up doing quite a bit. So get used to them. And we divide that up. So now we've got a handy dandy little table here to help us work our way through this problem. So what we're going to do is, when it comes to ice tables, it's important that we only put concentrations into these. We're always going to use concentrations only in ice tables. And there's a couple of reasons for that, and there's a couple of approaches, but I think overall our best bet is just to go ahead and make sure that we always put concentrations into ice tables. So one of the issues we run into here is we're not given a concentration, we're given a number of moles. But we are also given a volume. So before I put anything into the ice table, I'm actually going to turn this moles and this volume into a concentration. So hopefully this is something that is really becoming second nature to us at this point, but I'm going to do the concentration in moles per cubic decimeter, or molarity, same thing. So I'm going to take the number of moles of A, let's say, and divide it by the volume. And so I'm going to get a concentration of A initially, 0.250 divided by 2, that's 0.125. Concentration of A initially at 0.125 mole per cubic decimeter. So I'm going to go ahead and write that in there. Now that's my initial concentration of A. And if we notice B, the number of moles of A and B are the same. So B's concentration is going to be the same. Notice it doesn't say anything at all about AB initially. Well, that's because we were to assume, so the concentration of B is the same, we were supposed to assume that the concentration of AB is 0 initially. If there was any AB present initially, it would have had to have told us about that. But It didn't, so we can safely assume that there was no AB present initially. A mistake that I see people make, especially when we do later types of problems, is put X here, but this is not X. We do know that there is 0 AB present initially. Okay, and what I would suggest is, if you're a little unclear about where I got any numbers or how I got to this point where I did, maybe pause the video, back up a little bit, and make sure that you're on the same page with me before we go any further. So now what we're going to look at is, we're going to notice this reaction vessel that contains 0.236 moles of B. So it was discovered that the vessel contained 0.236 moles of B at equilibrium. There's those key words. So we do know one of the equilibrium amounts. This is huge when the problem tells us one of the amounts at equilibrium. It makes all the difference in the world in how we approach the problem. So we're given that amount at equilibrium, and we're given 0.236 moles of B. Now we face the same problem. We face the same problem in that, again, we have to put concentrations into our ice tables, not moles. Still is the same reaction vessel and everything. Everything's going on in the same little reaction vessel. So I'm going to go ahead and change that moles of B from the problem into a concentration by dividing by 2. So 0.236 divided by 2 is 0.118. That says mole per cubic decimeter, so that's my concentration of B. So I'm going to put my concentration of B right here. Okay. So let's just make sure we're heading towards what the problem wants us to do. Calculate the equilibrium concentrations of all species and the value of Kc at 25 degrees Celsius. This part, finding the value of Kc, that's going to be simple once we have these concentrations. The hard work is actually getting the concentrations. Now we've already found the equilibrium concentration of B. We did that already. It's right here. So what we got to try to do now is figure out the rest of this table and figure out what these other two concentrations are. So this is how we're going to do that. We're going to figure out what this change is. And a change is like a delta, right? We should do final minus initial. So 0.118 minus 0.125. And that comes out to 0.007. So negative, in fact. So my change here in B is negative 0.007. Now, just stop and think and make sure that this makes sense. I started off with 0.125 moles, or concentration. It went down by this much, and we're left with 0.118. So that's my change. 0.125 minus 0.007 equals this. Pretty clearly, hopefully, since A is starting off with the exact same number of moles. Actually, before I get to that, one thing that's really important when you're figuring out these ice tables is that the change has to go along with the mole ratio. So whatever's going on in this column right here, or this row I should say, has to match exactly with the mole ratio in the problem. So in this case, the mole ratio is 1 to 1 to 1. There's understood coefficients of 1 in front of everything. So that means my change has to follow exactly that mole ratio. Meaning, since it's 1 to 1, the change in C has to also be 0.007, negative. As far as AB goes, it also, again, 1 to 1 ratio here has to be 0.007. However, we do have to deduce one little thing in that these are reactants, okay, and we're starting off with 0 AB present initially. If the amount of reactants is going down, the only thing that could possibly be happening is the amount of product has to be going up, or vice versa. It's not always reactants turning into products in these equilibrium problems. Sometimes our product is turning back into reactants, but we know the amount of reactant went down, therefore the amount of product must have went up, so that's why this is positive. So, by the way, the reason these are all concentrations, and the reason we can do mole ratios with concentrations is anything that we would do to turn these concentrations back into moles, it would just sort of cancel out. So it's totally fine to do this mole ratio stuff with concentrations as opposed to moles. It all will work out in the end. So to find our equilibrium values here, we're starting off with 0 AB. Our change is 0.007. So then our final concentration of AB is going to be 0.007. And as far as A goes, same number of starting moles, so this is going to end up the same down here. And so there we go. We've got the first part done already. We've got our concentrations of all three species at equilibrium. So how I would write this probably is I'd say concentration of A is equal to the concentration of B, just because they happen to be the same, equals 0.118 mole per cubic decimeter. So that's my concentration of A and B. And then my concentration of AB is equal to 0.007. And again, mole per cubic decimeter. So if I was like writing my answer on an IB exam or something, this is probably how I'd write it right here. Because I'm telling the concentration of all species at equilibrium. That's what I was supposed to do. The last part here is to calculate Kc. So again, hopefully we remember this and we remember how we're going to do this. Now that we have these equilibrium concentrations, I'm going to write my equilibrium expression, products over reactants. There's no coefficients, so we don't have to worry about any powers or anything. And then just go ahead and pop in these numbers that I just figured out. 0.007, and then 0.118, 0.118. So from my equilibrium concentrations, which is part of what I was trying to solve, I can figure out my value for Kc, and that turns out to be 0.503. And remember, this is a unitless number. So that's the second thing I was trying to answer. Now if we sit and we contemplate everything, kind of linked to what we've learned before, the value of Kc is less than 1 here. So therefore it makes sense that we didn't get very much product. Remember, this would indicate that reactants are favored. So notice we started off with a pretty decent amount of reactant and we actually barely ended up making any product here. So it makes sense we have a Kc value of less than 1. The reactants clearly are favored. There's quite a bit more of them at equilibrium than product. So, that doesn't guarantee us that this answer is correct, but it does sort of make sense in light of everything that's going on with the problem. Okay, so that is problem 1. I'm going to do problem 2 here, but I'd suggest if you were a little especially lost on this one, it might be worthwhile to stop, back it up, and take another look. But we're going to go ahead and move on to problem 2. So problem 2, again, we're here on this page. We just finished this one. I'm going to zoom in here, enhance problem 2. Okay, there it is, enhanced. So, a scientist is mixing hydrogen gas and fluorine gas to produce gaseous hydrogen fluoride. Notice they haven't given us a chemical reaction here. She introduces 0.350 moles of hydrogen, 0.0667 moles of fluorine, and 0.01 moles of hydrogen fluoride into 1 cubic decimeter reaction vessel. So here, notice up to this point, we're being given our initial conditions. It says at equilibrium here, so then it's going to give us some equilibrium conditions. But let's tackle the first part. We have to be able to write this equation. Hydrogen gas, remember Mr. Brinkelhoff. Fluorine gas, remember Mr. Brinkelhoff. Hydrogen fluoride would be just that. Hydrogen's +1, fluorine's -1. Put a 2 in front of it to balance it. And then we make our ice table. So, something like this. And ice, Remember that stands for initial change and equilibrium. And now we got to start putting stuff that we know into the table here. Remember, we're going to put concentrations only into this table. Now, in this particular problem, they've been nice to us, and they've made it kind of easy in that the volume of the container is 1. So, for example, when I'm looking at the hydrogen, she introduces 0.0350 moles of hydrogen. It's in a 1 cubic decimeter reaction vessel, so the concentration is going to be the same as the number of moles. And we've seen some other problems where this is the case. So that's pretty handy. It makes it just slightly easier anyway, that we don't have to worry about that. So if we go ahead and just put in the moles, which is also the concentration since it's a 1 liter reaction vessel. Just getting these straight from the problem here, not having to do anything fancy. Okay, so there's our initial concentrations. So at equilibrium, again, it's huge, huge, huge that it's giving us an equilibrium concentration. There's going to be other problems where it doesn't. And the problem that some of you are going to run into is you're not going to pay attention to that kind of stuff. You're not going to read the problem. You're not going to read every detail and every word. And you're going to try to mix up these techniques that we use to solve these problems. But it's huge that it tells us an equilibrium value, 0.0189 moles of hydrogen fluoride. Okay, so that would be this. So clearly our amount of product has increased. Keep in mind, in these kind of problems, we've got reactions that can go back and forth. It's not necessarily true 100% of the time that the reaction is going to go forwards and make more product. This time it did. Our change, if we just subtract, if we don't see it, like a little delta, final minus initial, our change is positive 0.0089. Started off with this much, increased by this much, and I have that. Okay, so we've filled out that part of the table. The next thing you're always going to want to do is you're going to want to do the change next. We need to figure out the change. That's in these kind of problems, figuring out the change is always going to be kind of the middle step. We don't want to jump down to this too soon, or we're going to get confused and probably make a mistake. We're going to do the change first, and then we're going to be thinking mole ratio with this change. The mole ratio here is 1 to 1 to 2. And when you are doing this box, your ratio of these changes better darn well match the mole ratio, or you're doing it incorrectly. So, for instance, in this case, we have 0.0089 moles of HF. And whether you want to do it with a little dimensional analysis or whether you want to just think about it and kind of figure out what it would be, however you're going to do it, we need to have our change here be half as much as this because of the 2 to 1 mole ratio. Our mole of HF is going to cancel out there. So 0.0045 here. And this is going to decrease. This is negative, okay? The amount of product went up, it increased, so the amounts of the reactants have to go down. That's the only way that could possibly happen. If the amount of reactants went up, the amount of product went up, the amount of reactants must went down. And since the ratio of fluorine to hydrogen is 1 to 1, the change here must be the same, 0.0045. Okay, so again, if this change part is not clear to you, maybe you should back up and take another look at this, but just notice that once I figured out this change, everything else just matches the mole ratio. A 1 to 1 to 2 ratio is the same as 0.0045 to 0.0045 to 0.0089. Negatives here come from the fact that the reactants have to be going down while the product's going up. So now it's just basic arithmetic to figure out my change here. It's going to be this minus 0.0045, so that's 0.0623. Just subtracting these two values here. and then 0.0306. This minus this equals that. So I've done all the hard work on this problem already. What I need to do is actually really just write down the answers. That's the first part, and then figure out the second part. So calculate the equilibrium concentration of all species. Okay, I've got that. I just need to clarify it and write it down. And the value of Kc, so we're going to calculate that. So the concentration of hydrogen is 0.0306 mole per cubic decimeter. Coming from right there, the concentration of fluorine is 0.0623 mole per cubic decimeter, and the concentration of HF is 0.0189. And so then, to find the value of Kc, I write the equilibrium expression. Products goes on top. Coefficients become an exponent in this case of a 2. So then we plug in those concentrations. The real reason to put concentrations into an ice table is you must use concentrations at this stage. We could have done our ice table with moles, but then we'd have to make the conversion to concentrations here at this point. And it's my experience that people forget to do it quite often when you leave it till this stage of the problem. So for that reason and some other reasons, I think it's best just to leave everything in, or rather, have everything in concentrations kind of all the way through. Because if we're putting moles into this, we're doing it wrong. There's some cases where it doesn't make a difference, but it's a good idea. Let's just always put concentrations here, and let's always put concentrations into ice tables. So now it's just a matter of calculating that out. And we get 0.187. Unitless value makes sense. There's considerably more product around than reactant at equilibrium. So our answer kind of makes sense, and it seems like everything worked out. So what I'd like you to do right now is see if you can give number 3 a try. So number 3, if I have the right page, this is the correct page. I can't enhance on the number 3, sorry. But give number 3 a try. Take a look at this one. It's a very, very similar problem to number 2. So try that one, and even go ahead and try number 4. Don't be fooled by number 4. It's basically just a I guess an extension of problem 3. Number 4 doesn't require a new ice table or anything of that sort. So if you find yourself doing a new ice table on number 4, you're doing it wrong. So go ahead and pause the video for a second, give number 3 and 4 a shot, and then we'll come back and talk about that. But pause the video. Really do it. Really pause it. Okay, so here it is. Workbook, page 12, number 3. And we're going to kind of show this one line at a time. I know it might be a bit hard to see the writing here, but hopefully you can tell. So first of all, to get our initial concentrations, we're basically going to look directly at the problem, except one other thing. We need to remember it's a 5 cubic decimeter reaction vessel. So it tells me my 0.675 moles of iodine and 0.876 moles of hydrogen iodide, which is this. Got to divide both those by 5 to turn them into concentrations before we put them in the ice table. It doesn't say anything about the initial concentration of hydrogen, which means we're going to call that 0. So then it talks about the reaction being established and coming to equilibrium, and we got 0.886 moles of iodine gas, which again we need to divide by 5 to turn into a concentration. So once I realize that, I know that the change, subtract these two numbers, and I got that change. Okay, so let's talk a little bit about this line just to make sure that we're all on the same page here. Remember, this change is the thing that must follow the mole ratio. It's 1 to 1 to 2. So notice in this case the reaction actually proceeded backwards relative to how it's written here. The reaction proceeded this way. We have an increase of my reactant of 0.042. My other reactant has to increase by the same amount. It's impossible for it to do any other thing. The mole ratio is 1 to 1, so both my reactants are going to be going up by the same number of moles or concentration. So if that's true, my reactant, or my product here rather, has to be going down. And because the mole ratio is 1 to 2, that's why my change here is double the change of my reactants. It's also a negative change. Since my reactants are going up, it's like that teeter-totter thing. My reactants are going up, my product must be going down by that amount. It's impossible for it to work any other way. They move like a teeter-totter. So then, again, when we kind of go back and get all our equilibrium amounts, that's what we're looking at there. Just do the arithmetic here with the addition or subtraction. So once you get all that stuff, that's the hard part. The hard part's out of the way. Then we just need to get this equilibrium expression, and we need to write the equilibrium expression as normal and fill in the blanks with our equilibrium concentrations. We have to put concentrations into an equilibrium expression, and they have to be equilibrium amounts. So we put in our equilibrium amounts, and we end up getting 1.11 unitless number. So that's number 3. Number 4 is a relatively simple one compared to the ones that we've been working on so far, I would argue. We're going to start off, we're going to write the equilibrium expressions. It says the conditions are the same, so that means the Kc value is the same, the temperature must be the same, and presumably, I guess, the volume of the container must be the same. So it gives me these moles, it gives me amounts of hydrogen and iodine, which I again have to divide by 5 to turn into a concentration. We have to put concentrations into these things. So that's 0.0402 and 0.0248. That's not supposed to be another decimal there, over x squared. And we just need to solve that for x. Multiply both sides by 0.042 times 0.0248. So we end up getting that. Square root both sides. That's my concentration. And we get 0.0333. Okay, so that's 3 and 4. If you had any trouble with those, maybe go back and try to look at those. And I would suggest that you try problems 5 and 6. See if you get those figured out. Thanks for listening. Have a good day.